Hey guys, how's it going? We're going to be starting 12.1, day 1 today, and we're going to be talking about limits. Remember, we've talked about limits before, and we have said that the limit of a function is the value that a function approaches as x approaches a number, right? So for example, take a look at this function here, right? This curve here. So first of all, when we talk about curves in math or calculus, what we're talking about is the graph of any function. It doesn't really have to, mean curvy in any way. So let's take a look at this curve here, y equals f of x. And you see this is a decreasing linear graph. And here you have the value c on the x-axis. So that's the point x equals c. It could be x equals 2, x equals 7, whatever. So what we're going to do now is, suppose I'm right here. Okay, that's me. I'm going to be walking towards c from the left-hand side of c. And as I'm walking towards c, I want to keep my eye on the graph, and I want to sort of record what the graph is doing, how it's behaving. So right now when I'm here, I look up or down to find my graph, and notice that the graph is above my head. When I move further here, where's the graph now? It's over here. It's decreased a little bit. As I move further, closer to 0, the graph decreased a little bit more. As I move even closer to C, the graph, okay, we see it's continually going down. And so at this point here, I can make a conjecture and I say, okay, by the time I reach this point C, this graph is going to be decreasing, and it's going to reach a vertical height, a value of this point L, right? Okay, so now let's do the same thing, but from this side. So suppose I'm here now, okay? I look up and down to find my graph. Well, now the graph is below me. But as I approach C, what's happening to the graph now? It's not going down. Now the graph is increasing, right? If I move towards C a little bit more, the graph is higher up. If I'm here, oh, the graph is higher up. And so what do I see the graph doing? The graph is increasing. And so I say to myself, by the time I get to this value of C, the graph is going to keep increasing, and it will reach a value, a vertical value, a vertical height of L. So from the right-hand side, we said that as x approaches C from, the left-hand side, we're going to abbreviate LHS, left-hand side, very technical now. The graph f of x is approaching a value of L. Okay, so let's define that word now, value. In math, when we talk about value, we are talking about the y-coordinate, and that's just set in stone, and it doesn't change whether you're in the northern or the southern hemisphere. Okay? All right, so that's what we discovered from the left-hand side, that my graph was approaching a value of L. Well, what did we discover from the right-hand side? As x approaches C from the right-hand side, as my x values get closer and closer to C from the right-hand side, we see that the value of f of x is also going to approach L. And so now something beautiful is happening here, because as I approach C from the left-hand side, and as I approach C from the right-hand side, I see that the graph is reaching the same vertical point. I say that the limit of f of x as x approaches C is equal to L. All right, so this is the most important thing in calculus, probably. And so let's just pause here for a minute. What is a limit of a function? The limit of a function is that vertical value which it will reach as you move towards a point from the left and from the right-hand side. And now you probably have lots of questions and you're like, well, that's always going to happen. If you move towards a graph from the left side and from the right side, it's always going to reach the same point. But you know what? That's not necessarily the case. And this section is all about all of those different scenarios. So let's move on and let's do an actual example here. What we're going to do is we're going to estimate the limit of 4x minus 1. So this is your function, f of x. We're going to estimate the limit of this as x approaches 1, a negative 1. And we're going to do it using a graph. And then we're going to use a table of values to support our conjecture. Okay, so the first thing I'm going to do here is I'm going to graph this function, right? Y is equal to 4x plus 1. Seems easy enough. The y-intercept is 1. And now the slope is 4. So as I go up 4, I go over 1. Okay, and then as I go down 4 here, 1, 2, 3, 4, I go over 1. So that's what this graph is going to look like. Okay, very cool. Of course, we're going to use a ruler to do this. So what we're asked to find here is, what is the limit as x approaches negative 1? All right, so what I do first here is I go to x equals negative 1. That's here. And now I'm at x equals negative 1. Okay, so I say to myself, if I were walking over towards negative 1, let me use the same colors. If I were walking over towards negative 1 on the x-axis, and I look for my graph, when I'm here, the graph is below me, and as I get closer and closer to negative 1, the graph is increasing, and I say, okay, as I reach this point negative 1, my graph is going to increase to a vertical value of negative 3. And now what's going to happen if I approach that same point from the right-hand side? Well, here, if I'm here, the graph is above me. I get closer and closer, and the graph I see is decreasing, and then I say to myself, oh, as I approach this point negative 1, the graph is going to be decreasing until it reaches or gets close to a vertical height of negative 3. So because from the right-hand side and from the left-hand side, the graph is approaching the same value of negative 3, I say the limit of 4x plus 1 as x approaches negative 1 is equal to negative 3. Okay, now let's support our conjecture using a table of values. So what I do here is I make a table x and f of x. And this value here, x equals negative 1, goes right in the middle vertically. And so what I want to do here is I want to put points that are approaching negative 1. So as I'm so we got to look at this from the bottom up for first. As I'm approaching negative 1, right? So look at this. I have negative 0.9. Then I get closer to negative 1 and I get negative 0.999. And from the opposite side, I'm far away at negative 1.01. And then I get closer to at negative 1.0001. I'm approaching negative 1. Okay, so the blue represents the right-hand side, and the green represents the left-hand side. So what we're going to do here is we're going to evaluate f of x at these points. So I'm going to do, for the first one, let's say, I'm going to do 4 times negative 1.01 plus 1, and that's going to give me negative 3.04. When I evaluate it at negative 1.001, I'm going to get negative 3.004. So look at these values here. As I'm approaching negative 1, what are my y values approaching? Oh, it looks like it's approaching a value of 3, a negative 3, huh? Okay, so what about from here? At negative 0.999, I get negative 2.996. and then negative 2.96. So if I look at it upside down as I'm approaching, getting close to negative 1, my y values are getting closer and closer to negative 3. So look at that. From here and from here, my values, my y values are approaching negative 3. So I say the limit of 4x plus 1 as x approaches negative 1 is negative 3. Notice I didn't write anything here. And I didn't really talk about that point there either, at x equals negative 1. You know why? Because the limit doesn't care about that stuff. It's irrelevant what that point actually is. All we care about is what y value is it approaching from the left, what y value is it approaching from the right. And that's it. That's what a limit is. It's that term of approaching something. We don't really care whether we get there, when we get there, we don't care. Okay, so let's talk about a couple of things then, a couple of scenarios. There are 3 scenarios where this can happen. So look at this function here, okay? We have x equals c. Now, as I approach c, where is the graph? Here. The graph is decreasing to this point, L. From the opposite side, the graph is increasing to that point, L. Because the graph is approaching the same value of L from both sides, we say the limit is equal to L. Now, if I were to ask you, what is f of c? What is the actual value of f at x equals c? Well, there is a hole there. So f of c is undefined, right? So this is case number 1, where you have a limit, but f of c is undefined. Now let's go to the second example. Look at this one here. This is my point C. As I approach C from the left-hand side, the graph is approaching a value of L. As I approach C from the opposite side, the graph is approaching a value of L. So clearly, the limit of this function g of x exists and it's L. Now, what is g of c? This isn't f of x, this is g of x. What is g of c? What is the value of the function at c? Well, there's a hole here, but you know what? There is a point there at n, y equals n. So g of c is equal to n. Okay, so this is the second scenario, and we're going to go through these in a lot more detail in the coming days, where it's possible that the limit is one value and the f of x, f of c is another value. Here, look at this one. From the left-hand side, the graph is approaching L. From the right-hand side, the graph is approaching L. And now, what is h at that point? What is the value at c? That's also L. So what this illustrates is the fact that it is irrelevant what the value of the function is at x equals c. It has nothing to do with the limit. In other words, the value of the function can exist at x equals c. It can not exist at x equals c. It could be the same value of the limit. It could be another value as the limit. It really is independent. The limit does not care about the actual value of the function at that given point. Okay, we're going to come back to this tomorrow and the next day and the next day and the next day. All right, so let's take a look at this one. We're going to estimate the limit of this function using a graph. Okay, so we can do this in a couple of different ways. One way is you can plug that into your calculator and graph it. Another way is you can recognize that x squared minus 16 over x minus 4 is my function. And that is a rational function. And there is something funny about that point x equals 4? It is a discontinuity. But what kind of discontinuity is it? Well, let's see. If I factor the top, I realize that the top can cancel with the denominator. And so because this cancels, what do I know? I know that x equals 4 is a removable discontinuity. Okay, and what did my function reduce to? Just x plus 4. So when you graph this, it's going to be just the graph of x plus 4. So let's just graph x plus 4 here. 1, 2, 3, x plus 4, yes, that's the y-intercept. And then the slope is 1, so you go up 1 over 1. Now, there is a removable discontinuity at x equals 4, okay? Where is that discontinuity vertically? Well, if we put 4 in here, we get a value of 8. So at x equals 4, which is going to, and at y equals 8, there's going to be a discontinuity, a removable discontinuity. So that's what that graph looks like. Okay, so now what we're going to do is we're going to find the limit using a graph. And we're almost done. I have 30 more seconds to go here. So we need to find the limit as x equals 4. 1, 2, 3, 4. Now, another way you can do this is draw an imaginary line at x equals 4. And then say to yourself, immediately to the left of that line, what is the y value of the graph? Well, that's right here, and it's 8. Immediately to the right of that line, what is the y value of the graph? Well, that's right. I mean, that dot is tiny, right? This dot here is super, super tiny. Okay. So if you look at it that way, immediately to the right, what is the value of the graph? Well, it's 8 again, right? And so because the value of the graph is 8 immediately to the left and the right of that imaginary line, we say the limit of x squared minus 16 over x minus 4 is equal to 8. And now, if we wanted to support this conjecture numerically, what we would do is same sort of table. The value where I'm checking for the limit, x equals 4 is in the middle, and then, I'm getting numbers that are getting exceedingly close to or far away to that number. So at 3.99, f of x would be 7.99, 7.999, 8.001, 8.01. So as I approach 4 from one side, my y value is approaching 8. As I approach 4 from here, my y value is approaching 8. So the limit is equal to 8. Okay, so f of x has a limit. However, I know I said we're not going to plug in the actual value of x, but let's just do it in this case. Go ahead and plug x equals 4 into that function. What do you get? It's undefined. So that is an important point I want to score, right? So f of x has a limit. However, f of 4 is undefined, and that's okay. All right, so we're going to stop here. I have some instructions here for your homework. You can go ahead and do your homework from here. Thank you very much.